Thank you so much. Yes, thank you to Matthias and to Mahdi for inviting me to give this talk, and for Seraphine for dealing with the technology. I know that's a pain. I'm joining you from a distant reality here in New York State, where it's still relatively early in the morning. I'm trying to fly a lot less these days, so collectively here we've saved, over 2 tons of carbon emissions by allowing me to do this virtually. So I really appreciate that. And I'm sure the rapidly warming planet does too. I will just say I got up at 4 a.m. my time to join the workshop today. So if I look a little tired, that's why. But yes, today I would like to talk to you about some work that I've been doing on empirical evidence and its relationship to the topic of the workshop here. So I've been thinking that we really need a new account of what we mean by empirical. And I mean like all of us, all of us thinking about science in practice, about the epistemology of science, we need a new account. And this is because, the traditional empiricist account relies on the primacy of observation, but as is abundantly clear to all of you, I'm sure, science, especially contemporary science, does not. We use complicated instruments to learn about nature, telescopes and accelerators and all the rest of it. And this isn't really a matter of observing with the naked eyeball. And yet, this idea of observation in the traditional empiricist epistemology of science was doing something really important. It was playing this really important role in the epistemology of science for telling us about how we learn about the natural world. And so I think we need to do some work to replace it and to say something more applicable to science and practice about how it is that we hook ourselves up to the world. And I think, this doesn't just matter for philosophers, but we need, I feel like there's almost like a, no man behind the curtain kind of situation right now, because if the public asks us, for why we take our scientific results seriously, what's the justification behind our scientific results, I think at the moment we don't have this really nice epistemology of science to give them because we're missing this key component. So I've been working on this idea, and the sort of the project is to say, like, well, let's take the spirit of empiricism, as insisting that we learn about the world from the world by putting ourselves in touch with it in the right sort of way, and think about that in terms of empirical data, and then ask, well, what is it that makes data empirical? Like, what is it to be empirical data? And I've, in previous writings and talks, I've kind of said something like this. I've said that data are empirical with respect to some target. You have to specify the target. When there's an interpretation of the provenance of those data using the resources of an epistemic context, such that the data are products of causal interaction with that target. And I use that in this piece that I'm citing here from 2023 to make some arguments about, like, how it's important to specify the target when we're talking about different stuff, distant systems, and happy to talk about that more if you like. But I think, and this sort of first pass take is supposed to be, consistent and work in concert with this idea of empirical evidence that I published in 2018, where the thought is, like, the stuff that our theories are supposed to be consistent with, the material that we're accountable to when we say that a theory is empirically adequate, isn't just an empirical result, and it isn't our observations, but it's this kind of more complicated thing that I call enriched lines of evidence, and the whole evidential corpus is built up of a bunch of these things. And the idea is that, you have some empirical data that are produced by interaction with the world. And, those data are then, and we have, lots of information, hopefully, about how that data was produced in the first place. And then those initial data records are then usually processed in some complicated way these days. And there's a bunch of more information about how that happens. And you end up with some empirical result, but that empirical result can only be used as something to constrain theorizing when we consider it in the context of all this other information about what went into its production and processing. So the part that we're concerned with today is this initial piece where where the empirical data is produced by some kind of, from the world in some sense. So what's going on there? I've said in the past, it's under some interpretation, the provenance of empirical data involves causal interaction with the target, and that epistemic contexts supply the resources for identifying and interpreting those causal interactions. But can we say a little bit more about the causal production of empirical data than that? So I've embarked on a book project that's supposed to give a kind of more fleshed out empiricist philosophy of science, kind of that incorporates and is based on this idea of empirical evidence that I've developed. And this project is in its early stages. But one of the first things that I've set out to do is to deal with this question of what it means to be empirical, what it means for data to be empirical. And this is what I've got at the moment. I welcome your counterexamples, critiques, objections, modifications. This is a work in progress. But this is what I'm going to argue. I'll just read you the text now, and then I'm going to talk about it a bit more in the course of the talk. So what I've got is that data collected by a detector is empirical with respect to some source, if and only if it is the product of a process in which a conserved quantity has propagated from that source to the detector, or more likely, in which conserved quantities propagate from the source to the detector via various intermediaries in a multi-stage process. So I know it's a mouthful, but you'll see why I did it. So I'm going to argue, I'm wondering, if this view of what it means to be empirical is compatible with some of the realisms that you've been talking about in this really interesting workshop. I'm going to try and touch on that briefly too in this talk. But I do want to argue that this account of what it means to be empirical is also compatible with anti-realism. I count myself as an anti-realist. And the reason for that are just sort of the old arguments that we've been hearing all along about anti-realism, motivated mostly by epistemic humility, but that I nevertheless think are, remained independently compelling. So I'll come back to that at the end of the talk. Okay, I'll say a little bit more about the view of what it means to be empirical that I showed to you just now. I'll talk about it in the context of the example of solar neutrinos as discussed by Dudley Shapere, mention a few other details and implications of my account of the empirical, and then we'll get back to the question about realism and anti-realism and the connection to entity realism. Okay, so here's the thought. The really basic intuition is that data is empirical when it puts us in touch with the world in the right sort of way. And what I'm suggesting is that we understand the right sort of way as physical causation in the following sense: the propagation of a conserved quantity or quantities in stages from the part of the world we're studying to the detector that we use to gather the data. And this is, here's the cartoon version, right? Like if you're getting empirical data from the sun, something travels from the sun to your detector, and then those data then undergo further processing, and then you get some results at the end of the day, right? And the contrast I have in mind here, which is important for other aspects of my more general epistemology of science, which I can also talk about, is with virtual data. So I think it's really important that we keep in mind that we learn about the world from the world, right? That is the core commitment of a kind of really basic sense of empiricism that I think many of us share. And I think so. This is why it's so important to understand what we mean by empirical, so that we can, carefully kind of guard against confusing virtual data with empirical data, and to ensure that when we think we're learning about the world, we're really learning about the world. And of course, this contrast raises all kinds of interesting complications these days, in terms of hybrid results that combine virtual data and empirical data, and that's something that I'm also investigating as part of this larger project. But I still think it's useful to nevertheless keep this contrast in mind between empirical data, which come ultimately from the world, and virtual data, which of course come from computers in the world too, but not from the source in the world that we're trying to understand. Okay. And I recognize, and I want to acknowledge right up front, that talking about physical causation and causal processes and things in the world and distant reality, all of this might sound very strange coming from an empiricist. Empiricists have traditionally been allergic to causation. So I recognize that this is perhaps surprising, but I nevertheless truly believe I am an anti-realist and an empiricist, and I'll try and make that case at the end of the talk as well. Okay, so I don't know if this surprises you, but it kind of surprises me that there aren't really that many explicit accounts of what it means for what the empirical is, what it means for data to be empirical, for example, in the contemporary literature. I take this as surprising because, as I said, I think it is such a central and crucial idea for an epistemology of science that is like empiricist in a very common sense way. But we can imagine alternatives, and if you have others in mind from readings that you've done that I haven't come across yet, I'd love to hear about them too. Maybe you could contrast the view that I'm going to advocate for here with, a view of the empirical that involves the transmission of information rather than a kind of, emphasis on the physical process. Maybe you could imagine a view that emphasizes aboutness, or maybe there's a kind of relational view building on maybe something like what Leonelli is doing with data. I don't know. These are all kinds of things that we could pursue. I'll just mention two alternatives that I've come across that I think are particularly interesting. So there's this paper from 1991 from Matthias Kaiser called From Rocks to Graphs, which is really fun. And there he gives a view about, like what empirical evidence is supposed to be, that relies on these sort of simple acts of presentation, a sort of, it's empirical by ostension. Like, so you're just supposed to be able to sort of be there with the thing that you're and present it, as, and that constitutes it being empirical. So we're supposed to like gesture at the rock and say this rock here, or these spots on the screen there. And he takes that as the sort of base, element that we build upon in an epistemology of science. But I think that, there are problems with this view. I don't think it's in virtue of us standing in front of a screen and saying this spot's on the screen here that, this little smudge is empirical, is empirical data with respect to some, radio source picked up by the Arecibo Observatory when it existed. It's not because we can stand there and point at the smudge on the screen, right? It has something to do, my intuition is, right, with the fact that there's something that traveled from the radio source that has been processed in a certain way that is now appearing as the smudge on the screen. And so I think Kaiser's view puts the emphasis in the wrong place. There's also this really fun paper from Hasek Chang, who we were just speaking of. His ears are probably burning wherever he is right now, but Chang has this paper called something like, for an old school conception of observability. I think it was originally a PSA paper that got published in Proceedings. And the argument there is for a conception of observation that sticks really close to this original kind of empiricist version of observation as kind of sense perception. And he modifies it to accommodate the measurement of quantities such as temperature, and to our sensing and registering of qualities, such like it smells in this room or something like that. So he's interested in capturing those observations and measurements that he thinks don't necessarily originate from an object, but nevertheless ought to count as observations. So I think this is an interesting view to look at and a fun paper to read. He does accommodate instruments to a certain extent in the view. He says in this vein, we can regard an instrumentally registered quality as quasi-observable if the use of the instrument is de facto incorrigible and does not involve any interpretations that are considered optional. So the point of invoking, the point for the epistemology of science of invoking an old school conception of observation for Chang is this idea of incorrigibility, of some kind of like baseline, facts that we can then build upon. But I think, for the reasons that many critics have found that sort of, foundationalist approach to epistemology of science problematic in the context of the original, of the traditional empiricists, I think the same sort of criticisms arise here. So I'm not going to follow him with this view either. What I suggest that we do is take something like Salmon and Dowe's account of physical causation and use that as the basis for understanding the appropriate connection between what we're trying to learn about in the world and the way that we're detecting it, as giving us an account of what it means to be empirical. So this is a sort of, misuse of the original spirit of the account, or the merged version of these two accounts. Those projects were intended as accounts of all physical causation, right? And that's not at all what I'm endorsing here. I'm doing something much more limited and specific. I'm deploying this view in a limited context as a way of understanding the causal production of empirical data, and just that. And so I'm completely remaining agnostic about whether we can have a general account of physical causation. I just want to take this view and make it do something, namely give us a version of, give us an account of what it means to be empirical. Okay, and in particular, what I'm going to say leaves open the possibility that there are, that there's physics that we want to understand as causal that can't produce empirical data. So maybe there's stuff we want to talk about in general relativity and quantum theories that, physicists or we philosophers of science end up wanting to count as causal, but that isn't going to do the kind of thing that I think is required for producing empirical data. So these ideas might come apart in that way. Similarly, it might turn out that empirical data are produced by a process that doesn't count on as causal on your preferred account of causation. That could be a possibility too, depending on what you believe about causation. Just to say it again, all I want to do is take the Salmon and Dowe account and use it to give to explicate this idea, the central notion of what it means to be empirical. Okay, so the basic idea, as I'm sure you remember, is that physical causation is a process in which a conserved quantity is transmitted from one place in time to another. And Salmon famously contrasts this with a pseudo process. He gives the example, of a spotlight in a stadium that could travel fast, the spot on the stadium wall could travel faster than the speed of light, but that doesn't sort of violate causality or cause any problems because it's just a pseudo process. The causal process in that example has to do with the light traveling from the spotlight itself in the middle of the stadium to the stadium wall. So he's interested in tracking the transmission of conserved quantities. He says a process is causal if and only if it transmits a conserved quantity, and then Dowe explicates conserved quantity in the following way. He says a conserved quantity is any quantity that is governed by a conservation law, and current scientific theory is our best guide as to what these quantities are, quantities such as mass energy, linear momentum, and charge. And this is how I suggest the source and the detector should be connected in order for data to count as empirical. So Salmon, gives an account of what he means by transmission by appealing to Russell's at theory of motion, the sort of famous response that Russell had to Zeno's paradox. And it's this really kind of deflationary account where there's nothing more to the transmission of a conserved quantity from a point P to a point Q than at every stage of the process between P and Q, that every stage of the process between P and Q possesses that quantity. I think it's might just be better here to just sort of stick with Dowe's, naturalistic kind of spirit in understanding what we mean by conserved quantities, and just help ourselves to whatever, our best our best theories in science, our best physics tells us about how stuff is transmitted. So I think, rather than sort of getting on board with Salmon's inclusion of Russell's at theory of motion there in order to understand transmission, I would just say, let's appeal to physics to tell us how conserved quantities propagate through space-time, and just look to optics, quantum field theory, acoustics, mechanics, all the rest of it to figure out how that works in any context that we're particularly interested in. And I think this is in keeping with the spirit of the theory. So something I want to flag now, and I'll come back to you in a little bit after we talk about the neutrino case, is that it would be really nice, I think, if our account of what it means for data to be empirical could accommodate multi-stage processes, so that it doesn't have to be that there's just a conserved quantity that just propagates through space-time by itself, doing nothing, interacting with nothing, and that is necessary that's the only way that we can get empirical data is for there to be no interactions. I think that would be really unfortunate because even sort of very simple what I want to count as empirical data, like that you get with your camera that you use at home, or some microphone on this laptop right now that I'm using, that data is, goes through lots of causal processes, it goes through lots of stages, there's multiple interactions happening. And I think it would be nice for us to be able to allow that there are, these multiple stages and still count the data as empirical. So that's a sort of aspiration, and the worry, that what might speak against that aspiration is, I think, the strongest worry is something about inducing epistemic risk. Like once we start adding stages and layers and many interactions, doesn't that just sort of pile upon the assumptions and theories and models that we need to invoke in order to understand what's happening, and doesn't that sort of saddle us with undue epistemic risk and make our, we dilute the epistemic potency of this sort of data. So I'll come back to this in a little bit, but that's an issue here. Okay, so Yeah, so the thought is, again, this is just what I showed you before, that data collected by a detector is empirical with respect to some source, if and only if it's the product of a process in which a conserved quantity has propagated from that source to the detector, or more likely, this is the aspirational part, in which conserved quantities propagate from the source to the detector via various intermediaries in a multi-stage process. And I wanted to talk about this view in the context of a case that you're probably all familiar with, from Shapere's 1982 paper on observation, where he talks in great detail about the detection of solar neutrinos and gives us this by now quite famous rendition of what it means to be observed and observable. So on Shapere's view, X is directly observed if information is received by an appropriate receptor and that information is transmitted directly without interference to the receptor from the entity X, which is the source of the information. And as as is obvious to everybody, I'm sure, this is not the traditional empiricist account of observation. It allows him to say that the detection of solar neutrinos allowed us to directly observe the interior of the sun. And in the context of this experiment by Ray Davis Jr. in the Hope Stake mine, and this is Ray Davis swimming in the water of the of the mine as they're constructing the experiment, I guess. But the thought that so this experiment, if you're not familiar, is like a big tank in an old mine, and you just wait for neutrinos to arrive from the sun and interact with it. And the detection of solar neutrinos using this experiment, was the reason that he was awarded a quarter of the 2002 Nobel Prize in Physics for the detection of cosmic neutrinos. So this is this really amazing, interesting experiment that's been hugely influential. And for Shapere, this is a nice example of observation for him, because he says that the neutrinos produced in the core of the sun travel without further interactions to earthly detectors, unlike photons from the interior of the sun, which have this horrible, torturous path to get out to the surface of the sun and then make their way to our detectors. And he says, any information they carry is thus unaltered by interactions along the way, even when they come from the central regions of the sun. And so kind of unintuitively, the center of the sun is directly observable on Shapere's view. But as you may also be well aware, there's more to the story about solar neutrinos. So the Davis experiment, eventually led to the discovery of neutrino oscillations. And that was after Shapere's published, observation paper was published in 1982. But in the original paper, Shapere had suggested that, that oscillations were neutrinos to be the sort of thing that underwent oscillations that would count as interactions on par with interactions between two or more particles. And so that would sort of destroy the directness of the observation on his account. And as history turns out, neutrinos do oscillate, and so that is kind of a problem for this particular case on his account. But I also want to point out that, as Shapere, really painstakingly documents in the observation paper, the detector involved in this experiment and all of the physical processes that are involved in it is really quite complicated. It's not just that there's the neutrinos arrive and then the thing goes ding and now we know that there's neutrinos. It's there's all of this chemistry and stuff that has to happen to make that to register their presence in the detector. So I've put it all here because I can't remember all of these things. There's a crazy amount of steps that have to happen, but it has to do with the chlorine capturing the neutrinos and then it producing radioactive argon and then that decaying and it bubbling in a certain way to get to an electrode and then that being counted. And so there's all of these steps involved in the detector that are between like the production of the what I would call the empirical result at the end of this chain and the original registering of the neutrinos in their capture on chlorine by chlorine. So what I think we should say about this case is that, neutrinos provide us with empirical evidence regarding the interior of the sun. If we define the target in this case as the interior of the sun, I think we can say that we have empirical evidence with respect to that target. And that those, the data in this experiment, Davis's experiment, count as empirical because the neutrinos physically propagated from the center of the sun to the home stake detector. But it's, I think interesting to note that then there's a chain of interactions designed to register their presence in the detector, and that this chain can also be understood in terms of the propagation of conserved quantities. So there's still, we can still track all of that evolution as in terms of the physical processes that are involved. At no point are we just like simulating, whether the argon decays on a computer and then using that as, part of the information here. It's like a physical process through and through. So the data that were causally produced by a chain of processes here puts us in touch with a distant part of the world, namely the interior of the sun. And I think that, it's not obviously a good account of, it's not obviously a good case, it turns out, of direct observation on Shapere's account, but it can be accommodated by the account we're considering now of the causal production of data. Even now that we know neutrinos oscillate, and even if we think of neutrino oscillations as interactions, which I'm going to leave as a conditional statement there, and even if we consider the multi-stage causal process involved in the actual detector. And I raise that point because I think, there might be some sort of vagueness about when we, what we consider to be like the first production of data in this long chain of processes. And, so I think if it's important for the view to be able to accommodate multi-stages in the process. And I think, if that means that you could sort of count the first data registered, at different points in that chain of processes in the detector, and everything would still work out that this counts as empirical. Okay. That brings us back to the worry I foreshadowed earlier about epistemic, being saddled with epistemic risks by allowing all of these stages in a sort of like complicated causal chain on the way to the production of empirical data and empirical results. Doesn't this just require a whole bunch of other background knowledge? And I think that that's right, but I think that this is often a surmountable problem because, often, or at least sometimes we're in a good position to supply that background knowledge and that we're confident about the assumptions and the modeling that needs to happen in order to include complicated causal chains in our understanding of the empirical production of data. And I think there's a nice discussion of this in Jamie Elder's 2025 paper on direct and indirect detections, where even though she does ultimately think there's a epistemically meaningful way to distinguish between the two, she comes out as saying that, direct detections are not inherently better than indirect detections. And it really depends, in both cases, detection is a model-based inference, and in all cases, like how good that inference is depends on like how good, junk in, junk out, right? Like how good the assumptions that had to go into that modeling were in the first place. And Dana and I in our 2024 paper on observation and experiment make a kind of similar point when we're discussing the potential differences in epistemic superiority between observation and experiment. And just there also argue that, it what really matters is like how well you have, like how good your background knowledge is, like how well you have a grip on all of those assumptions that need to go into arriving at the full picture of maybe the complicated process that is involved in connecting data to the target. And in some cases, even though there may be lots of stages and lots of assumptions that need to be made, we have good grounds to make them. Okay, or similarly, the process could be really simple and you could be on really shaky ground to know what's happening. And so it's not the directness per se that makes the epistemic difference. That's the point. Okay, so I just want to briefly mention a couple other details that are related to this account of the causal production of data. And these are things that I discuss more in writing on this, but I just want to kind of mention them here in case they're bubbling to the surface for you as questions also. We could talk more about them as well. Okay, so here are all the things I'm going to tell you about. One is that I think this account, even though I've emphasized the fact that I want an account that can accommodate science and practice that is thoroughly instrument-ridden, the scientific apparatuses that we have today are important, ubiquitous, need to be part of our epistemology of science. But I also, think that this account can accommodate human perception as, delivering empirical data to us. And that's a good thing because, there are some, not all empirical data is observation by the human senses, but some of it is. And we want to be able to accommodate that stuff too. But, I think the story just sort of straightforwardly transfers there too. You're, in this case, you are the detector and you are put in touch with distant reality in the right sort of way by the propagation of some conserved quantity. And so just consider yourself the detector in those cases. Okay. And I want to flag a recent contribution to this literature by John Norton, which I think is, really very much in line with the sort of account that I'm giving here. And, for no small reason, John and he was my advisor at Pitt and we worked together for 6 years. And so we talked about this quite extensively. He's has this beautiful draft of a book about empiricism that you can see on his website now and get all the chapter drafts and everything. He has a chapter on physical processes as a way of understanding what it means to be empirical. And he discusses their, different physical processes that he thinks are relevant. So he gives the examples of the propagation of light, vibrational modes of wave production in media, physical conveyance like sampling, and gravitational waves. And he has some wonderful case studies to illustrate that and to show how it all works. And, like my view, he says that human sense organs are not needed for the implementation of experiential processes on his account, but that, but he also accommodates human senses in this view. So there are certainly differences between what I'm attempting to argue and what John's arguing, and a sort of difference in the style of the way that we're approaching this question. But there's also a lot of overlap here. And so I would point you to that as well. And I mentioned it in this part of the talk because John explicitly has picked out these physical processes as relevant for generating empirical data because, on the model of the human senses. So first, for sight and sound and smell. And then he adds gravitational waves because we can't sense that, but they're there too. So he's, directly inspired by the senses, and it's also giving an account of what it means to be empirical. That's very much in spirit with what I'm doing here. Okay, so I also want to say that this sort of account is, not just about passive observation or just passive detection, but could accommodate experimental data that involves manipulation and intervention too. I think I'll just state it. I'd have to argue this in more detail in another place, but like, I think we can still tell these same sort of stories about the propagation of conserved quantities. And that's good because we certainly want to incorporate, we want to be able to include experimental evidence also. There's probably something interesting to be said about how this account deals with like things, black things, or absorbers, shadows, absences, right? So, I've given you this picture of these two beautiful black cats having a conversation. And I think, okay, do we have empirical data from the cats? If they're like really very black and there isn't light traveling from their black fur, right? I think, yeah, we can accommodate this kind of, it's not that we can never learn about black cats or something, but, we have to be a little bit careful to say what exactly we're getting, what exactly is the empirical data here, what is being propagated from which target that we're receiving. So like maybe in this case, it's it's that little bit of light coming through the translucent fur there that's giving us information about the cat rather than the blackness of the cat, rather than the absence. Nothing from the absence is propagating, but nevertheless, we could have empirical data about these cats. So I think like dealing with these sorts of cases is going to end up looking like, really carefully specifying what the target is in the world that you're trying to learn about. And then, being very careful to articulate what is it that's traveling and what is it that we're detecting. And I think, an obvious case that we've already talked about in this workshop that Mahdi gave a talk on yesterday is of black holes. And, here I think we can say a sort of similar thing to the cats, like we're not getting the empirical data from the black hole itself. We're getting it from the accretion disk around it. Nevertheless, that's interesting for constraining our theories about black holes. And this is a tremendous achievement and should be taken very seriously. But we could still be careful about, what the target is here and what is being propagated and transmitted. So there's a really interesting paper that I've mentioned here by Skullberg and Elder on how to think about directness and indirectness and observation of black holes in various experiments that would be fun to look at if you haven't read that yet. But I think can be consistent with the things that I'm telling you here. Okay. I know I'm short on time, but I'll just want to mention, I think this view could also accommodate examples when the source is the detector. So one of the cases that I was thinking about, just because I had, friends who worked on it, was the Majorana demonstrator experiment, which also has to do with neutrinos, coincidentally. In that experiment, they're trying to figure out whether neutrinos are their own antiparticle, and the detector involves these like ultra pure germanium crystals, and you just wait around for decays in the crystals that might generate these very rare, if they exist, double neutrinoless beta decays, and use the germanium crystals themselves as the detector of those decays. And so, on its face, this is an example where the source is the detector, and I think we want to count the data as empirical. So what's going on here? I think you could probably just say something about like, the decay happens in one part of the detector and is registered in another part, and there's still propagation. I don't think there's any kind of like big, deep mystery here, but it is interesting that there are these cases. Probably good to say something. Okay. And then finally, I think this view can also accommodate something that was, raised in the literature that Salmon and Dowe produced on physical causation, about whether persistence should count as causation. And, so for example, Dowe endorsed persistence as causation, saying a spaceship not acted upon by any force could still sort of count as a causal process. And I think that I'm hoping that sort of my appeal to, whatever our best physical theories say about propagation to address this, addresses this issue and allows for, things just sort of hanging around, persisting in time to count as propagating through space-time in the right sort of way. So, a real example that I was thinking about is the free streaming of the cosmic microwave background photons, from the last scattering surface to detectors in satellites or on Earth. And, in that intervening time, right, where the photons are just free streaming and not interacting with anything, shouldn't that still count as, a causal process in the right sort of sense? And I think that, once we just help ourselves to our best physics to understand propagation, the answer comes out right there. Okay, so I've argued that we can replace the traditional role of observation in empiricist epistemology of science with an account of the empirical. I've argued that data is empirical when it puts us in touch with the world in the right sort of way, that this right sort of way is physical causation in the sense of Salmon and Dowe, the propagation of a conserved quantity or quantities in stages from the part of the world we're studying to the detector that we use to gather data. Our eyes and ears and hands can be detectors, but so can sophisticated instruments. And I think construing the epistemic input for empirical science in this way widens the scope of empiricism to accommodate much of our best contemporary science, while also clarifying why empirical data has such a special place in scientific research. It is the medium through which we gain access to nature. It's how we gain experience. And I just want to flag that, this account of what it means to be empirical for data, doesn't give us, just being empirical isn't sufficient for being good, right? You could have, really bad empirical evidence. This is just sort of this minimum bar for being empirical that I'm trying to describe here. And I think there's probably lots more that needs to be said about, what goes into evidence being good evidence in some context. And that's beyond the scope of this argument. All I want to do here is just give us some on bare bones, what do we mean by data being empirical? Okay, very, very briefly. I'm wondering if this view is compatible with the sort of realisms and realist stances that you all have been considering, both in this workshop and beyond. I think there are many questions that we could ask when we're thinking about maybe entity realist commitments. So is it that we must be realists about that which we manipulate, that realism is warranted about that which we manipulate, that we may be realists about that which we manipulate? When I think about hacking, I sort of think about, the little hacking on my shoulder speaking into my ear says, it would be foolish to use something as a tool and not be a realist about it, right? You're kind of crazy if you're using a hammer and you don't believe in hammers. Similarly, if you're good enough to set up to spray the electrons and do so in a repeatable way, blah, 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 it's kind of crazy not to believe in them as real. So I'm wondering, should we, with that sort of account, version of entity realism in mind, what should we say about the solar neutrino case? We didn't spray the solar neutrinos, but if you broaden the sort of sense of tool use beyond, anthropocentric physical manipulability, there's a sense in which we did use them to investigate the interior of the sun. So I'm curious about whether we think, must we or Davis have been a solar neutrino realist in this case? Would it have been foolish to have used them to investigate the interior of the sun and then refrained from being neutrino realists? And I think, your answers may vary on this, but what I've gathered from listening to you all at this workshop is that the commitment, what would be the content of that realism that we would be foolish not to adopt in this case? It strikes me as it's a really thin commitment. I gather that it wouldn't commit us to a rich theory of the entity. And in one sense, this is good because, it accommodates the capacity for lots of theory change. And that's especially good in the case of neutrinos, which we're still trying to understand. And there are many open questions remaining about neutrinos. And certainly in the context of the historical episode that I was describing, where the issue of neutrino oscillations was being resolved, this is a good thing that, the realist wouldn't be committed to a super rich theory of the entity. But then I worry, this goes back to some of Mauricio's comments from yesterday, that the realist commitment just ends up being too thin, that we're just committed to there existing something, which I don't find very satisfying. But maybe we could consider some of these weaker claims, are we warranted in realism about maybe just the causal efficacy of the neutrinos that's relevant to the experiment, this sort of really, really thin, maybe just slightly more contentful than something exists realist commitment, or even weaker than that, is it okay for us to be solar neutrino entity realists in virtue of this sort of case? And I think here the objection that Mauricio mentioned yesterday about the flectron might apply here, in the sense that in precisely the sense that he was discussing yesterday, that I won't repeat here. So I'm not even convinced that we sort of may be solar neutrino entity realists here in any kind of ontologically, metaphysically strong sense. But that's, that really depends on the context of your own realist position. And I wanted to point out that, several of you in talks at this workshop have sort of shied away from the point of that metaphysically rich ontological commitment, which I think is very interesting. And, just to give one example, in Mauricio's talk about his considered view yesterday, he was careful to emphasize that even the warrant that he thinks we can get is defeasible. And that's good because, that sort of warrant has been, we've seen it occur in history of science cases that were in fact defeated. So this is a really important and kind of central aspect of at least his perspective. So I think, where I end up is I'm at the level of the, deep metaphysical, ontological, fundamental commitments, I'm still an anti-realist, just for the same old reasons that people are usually anti-realists at that level, because of the pessimistic meta-induction, which I think can apply to entities too, because of the possibility of alternatives, and not just the ones that the evil demons cook up, but scientifically interesting alternatives that maybe we haven't thought of yet. And I think at bottom, this is just a point about our limited perspective on the universe and the epistemic humility that comes with that. So I think we should be anti-realists, but I think that doesn't mean that we can't understand a kind of epistemic progress in science and even across radical theory change. And that's something that I've talked about in this paper, Enriched Evidence, that I'd point you to if you're curious about that. Okay, so I had this whole plan to respond to this really interesting argument from Hadi about the inconsistency or the incoherence of being an anti-realist of the sort that I am, and talking about causal processes and empirical evidence in the way that I do. I'll just very briefly mention that my response to that charge of incoherence is that we're all here talking about presumptions or assumptions about causal processes, about entities, and that's even the case for Mahdi himself. So, of course, it's important to presume the existence of the entity that you think you're targeting in your, scientific research. So of course, it's important to presume the causal process that's connecting you to that target. But it is really very important that those are presumptions because they're defeasible. I think we should all be fallibilists, and many of us are fallibilists about this kind of thing. And in fact, it's as I've argued elsewhere, it's the fact that they're presumptions that can be changed that allows empirical evidence to persist across theory change by changing them and recovering the empirical evidence despite that change. So this is my final slide, I promise. I think, in my view, empiricism has two main commitments, the epistemic primacy of experience, and I think we can cash that out in terms of empirical evidence in the manner I've described, and anti-realism. And I think one can be anti-realist about everything I've discussed, including all the presumed connections between the world and the associated causal modeling involved. And it's my view that we should, in fact, be anti-realist about that stuff in the kind of fundamental question sense, simply out of epistemic humility. Okay, that's it. Thank you.